In this session, we'll provide an overview of several basic concepts of temperature sensors, then discuss each of the device types in this product family. Included are temperature sensors and switches, along with RTDs and thermocouples. This slide shows some of the basic concepts behind analog temperature sensing. Depending on the type of sensor element, the temperature of the element will determine the output voltage or the electrical resistance of the sensor. Some common types of sensors include silicon PN junctions, thermocouples, and RTDs. The output voltage, or the resistance in such elements, is often approximately proportional to temperature. Here is an example of a local analog temperature sensor. A local temperature sensor measures its own temperature. So if the sensor is located on a printed circuit board, its output will track the temperature of the board. An analog output temperature sensor produces an output voltage that is proportional to its temperature. This output voltage can be measured using an analog to digital converter, or ADC. The ADC can either be integrated into a microprocessor or is implemented in a separate IC. A digital temperature sensor includes the ADC on the chip. In many cases, the output data is formatted in degrees centigrade. Maxim offers digital temperature sensors with a variety of different digital interfaces. The interface types include SPI, I2C, one-wire, and PWM. Customers choose the device interface based on a variety of factors, including the number of wires available and matching interface types available in the host microcontroller. A remote temperature sensor allows measurement of temperature using a transistor external to the temperature sensor IC. This transistor is most often integrated onto the die of an external chip, usually a microprocessor, an FPGA, or an ASIC. These devices often dissipate significant power that needs to be monitored in order to detect unacceptably high temperatures. A remote temperature sensor can be very useful in detecting those high die temperatures quickly and allow the system to reduce power dissipation prior to catastrophic failure of the IC. The remote sensor can also be used to measure the temperature of a discrete transistor that might be located near a hot spot in the board. There are several key specifications that are a concern to customers. Accuracy is an important one. Even when the customer doesn't need particularly good accuracy, it's important to understand their requirements, since better accuracy can often result in a higher price. Along with the basic accuracy, the temperature range over which the accuracy specification applies is important. Some applications require very good accuracy over a wide temperature range, while others require the best accuracy over a relatively narrow range. In the example shown here, the temperature sensor error specifications are listed for different temperature ranges. Other important specifications include the operating voltage range, power supply current requirements, and the operating temperature range. Many available temperature sensors have operating voltages in the 3 volt to 5 volt range, and it is not uncommon to find operating ranges that extend below 2 volts as well. Operating supply currents can range from a few microamps at low conversion rates up to a few hundred microamps. Some sensors are designed for excellent accuracy over a wide range of temperatures, while others are optimized for best accuracy over a limited range, such as near room temperature. Many thermal measurement devices include features above and beyond the basic temperature measurement functionality. While the most common ones are shown here, you'll encounter a number of interesting and unique features beyond those as you begin looking at specific devices. A remote temperature sensor may have one or more channels of remote sensing. Multi-channel remote temperature sensors may be useful in cases where there are multiple sensing transistors on a single board. Sensor resolution determines the granularity to which a temperature value may be expressed. General purpose applications may be able to use sensors with 1 degree C of resolution, while some designs require resolution on the order of 0.125 degrees C or less. An alert output that indicates an over-temperature or under-temperature condition can be useful when a temperature sensor is used as a system protection device. The DS1775R is a good example of a small, low-cost, general-purpose temperature sensor. The temperature accuracy is typical of many general-purpose temperature sensor chips. There is an output that provides an over-temperature alarm function. The I2C interface is also typical of many general-purpose sensors, although similar devices which implement SPI and other interface types are also available. A temperature switch is essentially a temperature sensor and a comparator. It provides an indication that the temperature has exceeded a preset trip threshold. Some temperature switches have fixed trip thresholds, while others have programmable thresholds. Most temperature switches use local sensing, although a few are able to sense the temperature of remote diodes. The MAX 6501 and 6509 are two popular temperature switches. The MAX 6501 has factory preset thresholds. While the base part number is MAX 6501, it is available in over a dozen versions or part number variants. Each variant has a different temperature trip point. In contrast, the MAX 6509 features a programmable trip temperature. That temperature is set by the customer using an external resistor to set the trip threshold. The value of that resistor is determined from a formula, table, or curve in the datasheet, which correlates trip temperature to resistor value. Products like these are commonly used as over-temperature protection devices that can help shut down the system when the temperature exceeds a predetermined limit. In practice, it's useful for a temperature switch to include some hysteresis around the trip threshold. This prevents chattering of the over-temperature output. As mentioned earlier, the output might be used to shut a system down. It could also be used to signal a microcontroller that excessively high temperature has been detected, or to enable a cooling fan. Thus far, we've talked a lot about temperature measurement devices which use silicon as the basic sensing element. Silicon sensors have many positive attributes, and Maxim has been building devices based on silicon devices for many years. However, sometimes customers want to measure temperature using a different type of sensor. Very often, that is a thermocouple or an RTD. Why would a customer want to use a thermocouple or an RTD? The main reasons have to do with temperature range. A silicon sensor will work between minus 55 degrees C and plus 150 degrees C at most. There may be a few exceptions to that, but for the most part, that's the range that you're stuck with if you're working with silicon. A platinum RTD will work from minus 200 degrees C, or perhaps even a bit lower, up to around 850 degrees C. There are a few that are rated as high as 1,000 degrees C, although those tend to be a bit specialized. Thermocouples will go even farther than RTDs, measuring down to absolute zero and all the way up to 1,800 degrees C. So if you're measuring very extreme temperatures, you'll probably use a thermocouple. If the measurement range is a bit less extreme, you'll probably use an RTD. Another reason to use a thermocouple or an RTD are that they are fairly replaceable since many follow industry standards. There are RTDs that are referred to by certain names because they follow certain characteristics. RTDs are also extremely repeatable. Thermocouples are extremely rugged since they are simply two wires which are soldered or crimped together. This ruggedness plays a part in their popularity. Another reason for their wide use is that they are available in a variety of form factors, such as probes. This choice of form factors is generally not available with silicon temperature sensors. An RTD is typically a platinum resistor. There are other metals that are used, such as nickel and copper, but platinum is by far the most common. The resistance varies by roughly 0.4% per degree centigrade with respect to the 0 degree resistance. They are often referred to by the standard names PT100 or PT1000. The numbers 100 and 1000 in those names refer to the resistance at 0 degrees C. A PT100 RTD is 100 ohms at 0 degrees C, and the PT1000 is 1000 ohms at 0 degrees C. RTDs have a wide measurement range and are very repeatable. RTDs are available in 2, 3, and 4-wire versions. The 2-wire version provides one connection to each terminal of the resistor and is used for both exciting it with a stimulus or voltage and also measuring the result. This works well when the sensor is close to the measurement circuit. When the sensor is farther away from the measurement circuit, the longer lead length can affect the measurement because it's going to add extra resistance. So as you get farther away, you need to look at using either 3 or 4-wire devices. These extra wires are used to separate the excitation signal from the measurement signal, allowing either partial or full Kelvin measurements. This serves to eliminate the effects and errors associated with lead resistances. There are 2 basic approaches to acquiring the signals using RTDs or thermocouples. You can design the circuit from scratch using a discrete ADC as the heart of the measurement system. This has tended to be the industry standard approach. Using an ADC which is optimized for sensor applications can result in very good performance. This method can also be very flexible since it is possible to have a single device that can be configured for a variety of RTDs and a variety of thermocouples. While Maxim does offer several high-performance ADCs well suited to this approach, we also have some dedicated thermocouple to digital and RTD to digital chips. Those are pretty handy for customers that want to get something up and running fairly quickly and may not be very familiar with the characteristics of these types of sensors. These devices provide a way to get a completed design in the shortest amount of time. They also solve a lot of design problems that are inherent with these sensor types that the customer would normally spend a lot of time solving using a discrete approach. So these ICs reduce the customer's design time and cost while providing a high level of performance. Maxim introduced the MAX 31865 single-chip RTD digitizer several years ago. This device offers a simple and accurate way to measure temperature using RTDs. The device measures the resistance of the RTD by forcing a voltage across a series combination of a reference resistor and the RTD. The voltage on the reference resistor acts as the reference for the internal ADC. The voltage across the RTD is then what is being measured. Therefore, the data out is the ratio of the RTD resistance to the reference resistance. The corresponding temperature is calculated from the value of the RTD resistance. This device is fairly accurate, having an error of less than 0.5 degrees C. And under most conditions, it typically performs better than that. RTDs are frequently used in factory environments where the sensor is connected to the measurement circuitry with long cables, which can get shorted to a power supply voltage. This device incorporates protection against an overvoltage between plus and minus 45 volts on the inputs, which might destroy a measuring circuit based on a typical low voltage ADC where this type of protection has not been included. It also detects a variety of fault conditions, such as opens and shorts. Incorporating these fault detection functions can be fairly tricky to implement on a measurement circuit based on a discrete ADC. So while the basic measurement circuit might be fairly straightforward, the implementation of a complete measurement system, which includes the fault protection and detection features necessary to survive in real-world applications, is much more of a challenge. The MAX 31865 offers an accurate, reliable, and proven solution which is easy for the customer to quickly incorporate into his system. Thermocouples are pretty useful devices because they handle the widest temperature range of the devices we've discussed. It was discovered in the early 1800s that when two different metals are joined together, a very low voltage is generated. This voltage is on the order of microvolts, and the actual value depends on types of metals used to form the junction. Due to its simplicity of construction, thermocouples are very rugged and serve well in measuring temperatures in both physical and electrically harsh environments. However, implementing a practical measuring system based on thermocouples has its challenges, which you'll see on the next slide. The output signal from a thermocouple is a voltage, as opposed to the resistance output we saw with RTDs. And that output voltage is very low, on the order of microvolts per degree centigrade. Since the output voltage is so low, the thermocouple voltage is generally amplified before it is measured by an ADC. And again, since the voltage is so low, that amplifier must have a very low offset voltage. Common general-purpose op-amps have offset voltages in the 1 millivolt range, but an op-amp used in this application requires a much better specification, generally in the range of 10 to 70 microvolts. And that amplifier will need a gain of roughly 32 to 128, and that gain must be fairly accurate. The requirement for accuracy doesn't end with the input amplifier, but extends to the rest of the signal measurement chain. That includes the ADC and the voltage reference feeding the ADC. This requirement for accuracy and precision makes the design of the overall analog signal chain tricky, requiring a very careful design and close attention to the error budget. Another issue to be considered is electrical noise. Since the thermocouple voltage output is so low, even small amounts of noise that are picked up on the input leads will have a detrimental effect on the measurement. Thermocouple leads are often shielded if the lead length is very long, or if the measurement environment is particularly noisy. The relationship between temperature and output voltage for a thermocouple is fairly nonlinear. In the curve to the right, it's fairly obvious that the portion of the curve on the lower left is quite nonlinear. If you look carefully, you can also see nonlinearities in the rest of the curve. As a result, any system which uses a thermocouple as its measuring device will require some mechanism to compensate for these nonlinearities. This compensation is resolved with a 12th order polynomial, a CPU-intensive calculation that is difficult for slower processors. This is often simplified by the use of a lookup table. Although not always the case, thermocouples are often to be used in uncontrolled and sometimes hostile environments, such as factories or remote field locations. They can be connected by long cables which are exposed to vibration and the potential for accidents such as broken or disconnected cables and shorts to ground or high voltages. The measuring circuit must be able to reject noise, detect broken wires, and protect against shorts to high voltages. Another challenge associated with thermocouples is the requirement for something called cold junction compensation. As we discussed, a thermocouple is a junction of two dissimilar metals. In fact, any junction of two metals will result in a thermocouple, and that includes places where we don't really want one. In the diagram, at the far left is the thermocouple that is placed at the point where we want to measure the temperature. Following the definition of a thermocouple, it is formed by the junction of metal A and metal B. As a result, it will generate a small voltage, which is the voltage we want to quantify to determine the temperature. However, if we look at the point where the two wires connect to the measuring circuit, we see that we have two additional junctions of two dissimilar metals. One is formed by the junction of metal A and the copper trace on the printed circuit board. The other is formed by the junction of metal B and another copper trace. Both these voltages will add to the voltage we want to measure, the voltage from thermocouple 1. Also, note that both these unwanted thermocouples are located at the two-terminal connector, often located in close proximity to the measuring circuit. To account for these unwanted voltages, it's necessary to subtract them from the voltage presented to the measuring circuit. This process is called cold junction compensation. Before the advent of low-cost temperature sensors, the approach taken was to keep the two unwanted thermocouples at a constant temperature, typically using an ice bath. Then, the voltage generated by both the unwanted thermocouples is known and can be subtracted from the total voltage presented to the measuring circuit. The temperature at thermocouple 1 can then be calculated from the resulting net voltage. Of course, implementing an ice bath is both expensive and impractical in most situations. Since low-cost silicon temperature sensors are readily available, it is much simpler to measure the temperature at the connector, then calculate the voltages generated by the unwanted thermocouples. It is certainly possible to build a complete thermocouple measurement system using discrete components. In fact, that was the only alternative until fairly recently. However, it is a fairly tricky design, especially when the product will be used in electrically and physically harsh environments. Most of the reasons for this complexity were discussed a couple slides ago. Here's a list of all those reasons. The combination of very low-level signals from the sensors, often measured in an electrically noisy environment, combined with the often necessary requirement to protect the system from hazards and faults, creates a design challenge often beyond the skill level of the average engineer. And even if the engineer has the skill to implement the design cycle can be lengthy and will often result in a large and expensive circuit. Fortunately, alternatives have become available. Maxim has produced single-chip thermocouple interfaces, often called thermocouple digitizers, since 2002. In 2011, we introduced the MAX 31855, a device that provides a direct interface to thermocouples and produces a digital output representing temperature. That included the front-end analog circuitry, cold junction compensation, and detected opens and shorts. When using this device, linearization is performed by the host microcontroller. That part was offered in a number of versions, each one dedicated to a specific thermocouple type. Overall accuracy of the MAX 31855 is roughly plus or minus 4 degrees C when all errors are taken into account. The successor to that device is shown here, the MAX 31856. This device offers a number of improvements over its predecessor. It can interface to 8 different thermocouple types, while the MAX 31855 required a different IC when changing from one thermocouple type to another. This device also handles the linearization internally, relieving the microcontroller of that burden. Accuracy is improved and is roughly 2 times better than the MAX 31855. Inputs are protected to plus or minus 45 volts. Finally, a notch filter can be enabled to eliminate noise at 50 and 60 Hz. While thermocouple interfaces can be implemented using a discrete approach, the MAX 31856 offers a high incentive for designers to solve their measurement problems with a single monolithic part. This is appealing to any customer who wants to reduce their design cycle, reduce board space, or simply doesn't have the expertise to consider the discrete approach.
To summarize, in this course we have given an overview of several basic concepts of temp sensors, discussed temperature sensors and switches, along with RTDs and thermocouples. For more information on this topic, please go to our website at www.maximintegrated.com under Products, Sensors, and Temperature Sensors. We hope you enjoy this video and see you again in another educational video of Maxim Integrated.